Okay, guys, I put the final homework on Canvas. You don't have to submit anything, but do it because the material will be on the final. Um, by the way, really nice presentations yesterday. It, I've seen 2 years. This was probably the nicest year. This was my third year. Yeah, it was really nice. Hopefully, you all reach out to all the people who were impressed from Lockheed Martin and all these places. So it was very nice. Oh, and today's your last day as students, or most of you. We miss it? No. Okay, you will miss it. Give it. Give it 4 or 5 months. You'll miss it. Yeah. Okay. All right. So yeah, today we'll finish talking about wave drag and how ships, well, what we can do to reduce the effects of wave drag. So this is where we started. Wave system created by a point pressure source, right? It was Kelvin said, okay, if you have a single pressure point that's moving, it'll create these two types of waves, diverging and transverse. And we said that, okay, these transverse waves move with the ship, so their speed has to equal the speed of the ship. If we know that, we can predict what their wavelength will be. Okay, and that's just a recap from what we know from wave mechanics. So the wave system I drew on the previous page was for a single point source. Okay, but for a hull, we get a slightly different pattern. So this is what it looks like. Okay, so let's say this is our hull. Okay, so the biggest difference will be there will be two wave systems created, one at the bow and another at the stern. So let me try and draw these two different. We'll have one wave system like this. Right. So, and then we have one system at the stern. They will both have the same wavelength, but the biggest difference is, okay, think about this. When you see a boat moving through water, what do you see at the bow? What happens to the wave that's generated? You see a crest or a trough? Yeah, at the front, like at the bow. So you say crest, you say trough. The what? The bulbous? Um, it makes a crest because you're basically pushing water away, so the water rises up, right? So you get this crest. that's generated at the bow, and it starts moving back. So that's what happens right here. Okay.
Talking about on the waterline, or like not on the bottom?
Oh no, on the surface. No, we're talking about the waves you generate on the surface, right? So that's what wave making drag relates to. At the stern, the opposite happens. Okay, so the wave system you create is actually has a trough right at the stern. Okay, and then it propagates backward. So, do you remember what happens when two waves combine? The amplitude. What happens to the amplitude? If you have two waves, two sine waves, and you add them together.
The amplitudes just combine. They add.
The resultant amplitude depends on what's the phase difference between the two waves, right? If the two waves are synchronized, then the resulting amplitude will be higher. If the two waves are opposite in sign, they can cancel each other out. Okay, so
you get an interference pattern is what you get.
Yeah, you get constructive interference and you get destructive interference. And based on which one we get, we waste more energy or we waste less energy. Okay, so we'll talk about all of that in detail. So first, let me point out that these all right, so let me also write out the details we talked about. So for real hulls, or for hulls, the bow and stern. Okay, and the reason is here you're at the bow, you're pushing water away when your boat is moving forward. But at the stern, you know, this, if you remember streamlines, the water tries to come back in and creates a wake. So that gives rise to the trough. So so if I just draw some crude streamlines, when you have water here, you're pushing it away. And as you come back here, it gets pulled back in, not as nicely, but you generate a wake. Okay. And when these crests and troughs, they combine, you get constructive or destructive interference. So does this make sense? I mean, why would, I mean, I told you that bow always creates a crest and the stern always creates a trough. So it should always be a crest and a trough combining. So it's a destructive interference. So why am I talking about? There can be different scenarios.
I'm guessing that the phase angle between them will have to do with the length of the ship versus the velocity of the ship.
Yeah, so remember the wavelength depends on how fast our ship is going. But the length of the ship itself is fixed. So depending on what the wavelength is, you have a different number of waves along the length of the ship. So if you go faster, the wavelength becomes longer. So you see at some point, the crest you are creating here will coincide with the trough. But at other points, at other speeds, the trough system that's generated by this will coincide with the trough here, which is bad, okay? So that's how we get constructive and destructive interference. I'll show you the image I sent you guys today, and it'll help make it clearer. So okay, and when the two crests coincide, the resulting crest has 2 times the height. So the resulting wave
Will the amplitudes of both the wave systems be the same?
No, they're not the same. So when I said 2 times the height, that was assuming they're both the same, like sine waves or of the same amplitude. So that's why I wrote that the resulting height will be larger. It won't be exactly double. The bow system is slightly weaker compared to the bow system is stronger compared to the stern system. Do you remember energy for a wave? Depends on what? The height? Height is basically amplitude 2 times, right?
Yeah, because now
If you remember from wave mechanics, rho g(h) squared over 8. So the energy only depends on h squared, nothing else, not on wavelength, not on the time period. Okay. So when we get a larger height, you're basically creating waves that have much more energy, h squared, right? So all this energy is getting wasted now. So did you guys learn about hull speed in fluid mechanics? No. Okay, let me. Fluids 1 year ago. Okay, so see, this is, well, let me see if we have a cartoon. Okay, maybe this is good enough. No. Okay, so let's see. Okay, this picture is more or less what we're what's related to hull speed. So you see, there's like an upwelling at the bow and an upwelling at the crest. So this is a very specific speed, right? If your boat starts going faster, what will happen? This upwelling will be behind the boat, right? If you're slower, then instead of one full sine wave, you get multiple sine waves inside. Okay, so this instance is called the hull speed. Okay, and this is one of the most efficient speeds to go at. Okay, because okay, you tell me why. Because why is this a good state to be in? The two what? Yeah, the bow wave is the one we see here, right? The bow generates this upwelling, downwelling, upwelling. So one full sine wave sort of. And the bow wave's crest here will coincide with the trough that the stern generates. So they'll cancel each other out. So the wave that you leave behind in your wake is very tiny. Okay, so that's good because you're not wasting as much energy. So that's the main concept of hull speed. Okay, and if you go faster, what happens to your drag? It's going to ride.
Instead of it being perfect, it's going to kind of get on top of that bow.
Okay, it's going to start planing, right? Your bow will rise out and your stern will dip. Will your drag increase or decrease? Depends.
It depends on the shape of the bowl.
Okay.
If it's designed to be boat,
yeah, if you have a cargo container, cargo ship that starts planing, hopefully never happens. Yeah, so that design is terrible for planing. So hulls that are designed specifically for planing will reduce wave drag. Okay. What if you go slower and you have multiple waves along the hull? What happens to your drag? Is it like constant throughout? Does it increase linearly? was increase. So, yeah.
Surface area is never changing.
Yeah, the surface area doesn't change, or just the wave making drag changes. Does the wave making drag increase or decrease when you start going slower than hull speed? It does both, right? Depending on if you start going slower, you'll generate multiple waves. So at some point, you'll generate 2 full waves, which is nice, right? Because you again have a crest combining with a trough. If you generate 1.5 waves, that's a bad situation because your trough will combine with the trough. So in the curve for drag, you get these humps. When you make the curve, you get these humps and hollow. That's the technical term for the change in drag. Okay, and you can decide what is the speed your boat should run at to not be on the, you want to be in the hollow, low drag. Okay, so let me draw a sketch and it'll become clearer. Okay, let me write a few things first. Constructive, then destructive. Okay, and as we were saying, as you change the ship speed, let's say you start from S, and as Okay, if I make a sketch of resistance curve, okay, when the ship is not moving, obviously the drag is 0. So our curve starts at 0 and starts increasing as the speed increases. All right, and you'll notice at some point you'll get this sort of a hump and a hollow and a hump and a hollow. Okay. So now conceptually, do you understand the reason for these to exist, the humps and the hollows? No, not yet. Okay, okay. Okay. So let's take a look at this image, and I'll bring this back again. So let's see. Let's say you're going very, very. Are you able to read this? On the screen, is this visible? The text? Okay, let me zoom in a bit. All right. So your boat has just started moving and it's going relatively slow. Okay, meaning the if your speed low v will give you low lambda, right? What was it? 2 pi v squared? Yeah. Oh, sorry.
Yeah.
For small speeds, you'll get small wavelengths. Small wavelength, right? That's what the wavelength is, from crest to crest or trough to trough. If you have small wavelength, meaning you have these multiple waves, okay? But as you start speeding up, let's see, how many waves are there? There's 1 full wave, 2 full waves, 3 full waves, roughly 3.5 waves along the whole hull. As you start speeding up, what happens? Your wavelength starts increasing, okay? So you get fewer waves along the hull. At some point, let's say at this instance, what do we see? We see a crest from the bow has reached the stern. So at this point, we'll get which one, hump or hollow? We will get a hump or a hollow in the drag. Drag will increase or decrease? Crest from the bow is combining with trough from the stern. Yeah, that's good for us, right? That the drag decreases, okay? So that's what this hollow represents, okay? Since we are talking about the ship speed here. Now let's go even faster. So we go even slightly faster, and from here to here, let's see what happened. Now we have 1.5 waves along the hull. And this is a very bad situation. Our bow's trough coincides with the trough that the stern will create. So not good. here you get a sudden jump in the drag. So we go from this hollow up to this hump. Okay. So hopefully now it's makes sense what the humps and hollows represent. Okay. So whenever you operate a ship, it's very useful to have this sort of curve handy. So you can decide, okay, I'm going, let's say 20 knots, I'm here. If I increase to 22 knots, I'll suddenly jump to here. Is it worth it to go faster? I mean, you go faster, but your power consumption increases substantially. Okay. So it's a trade-off. 20 knots here, 22 knots there. What would you do if you were at this situation? Yeah, you can slow back down, or you can go even faster. So if you go faster, you're not consuming any more fuel. Your drag doesn't increase, but you cover more distance in the same time. So knowing this sort of a curve helps you optimize your speed and drag. Okay. And all of this is due to wave drag. You can, if you know the length of the boat, you can predict what the hull speed is. If you know the length of the boat, you can see when you know the speed you want to go at, you can predict the lambda. If you know the lambda, you can predict when the thing will coincide constructively or destructively, right? So that's a, does that make sense? If you know your speed you're going at, you know lambda, you can count the number of waves along the hull because you know the length. And then you can adjust the speed to make lambda larger or smaller to achieve the destructive interference that's beneficial.
What's the FN number?
This is Froude number. Yeah, I don't know why I use FN. So here, the FN they use is basically our Froude number. Yeah, we use FR. I'll show you how they say this so confidently that Froude number is 0.28 for this to happen. Okay, we can show that. Okay, I'll bring this back. Okay, let me write a few things here. So that's the total drag. Okay, now you can break this graph up further, right? This is the total contribution from friction, from wind resistance, from wave making drag, and we can look at all of those things independently. So if we just break this down, Okay, so this curve I had on the top of the page, if we break it down, it just gives us this. Okay, so hopefully this makes sense. I mean, the viscous resistance will not, we treat it independently of the wave making. So no humps and hollows here. And for the wave making, we do get these humps and hollows with the change in speed. And when we add all of these up, 3 contributions up, we end up at the total resistance curve. Okay. Air resistance is constant with speed. Oh, I've drawn a sketch, but so think of this. Yeah, it changes with the speed because think of your car moving through air. The drag scales as v squared. Okay, so yeah, it's not everything keeps increasing with speed. And again, viscous, I've drawn a straight line, but it's not really a straight line. It's just to show you how things break up. Okay, and all of this is related to the image, which I'll bring back. Where is it? Okay, here. So I sent you this, and you can just write on it if you like. So these are wave patterns along the hull at various speeds. Okay, and we already talked about what happens as we change the speed. So let me write a few sentences, and then we'll come back to what the Froude number, how we compute the Froude number here. Okay, so Okay, let's pick a specific example. So this guy, when lambda is exactly half of the of the hull length. Okay, so we expect to get 2 full waves along the hull. All right, so okay, if you know the lambda, if I give you the lambda of the wave, what can you tell me? You can tell me the speed of the boat, right? The speed it's going at. So we can determine all right. How do we determine the Froude number? What do you need to determine the Froude number? Yeah, speed and the length, and both of them, we have a relation between the two, right? So it should be doable now. So Froude number we know is u divided by square root of GL. Okay, and we just determine speed. So we have 0.8835 square root of L, square root of GL. Okay, you see all the unknowns go away, and we have a constant 0.2821. Okay, and this is exactly the number mentioned in the image here. For half weight, half length, we get root number is 0.28. Okay, you can do the same for any of these cases, and you'll be able to determine the corresponding Froude number. Okay. All right, now one thing to notice here, yeah. We said this is a very good situation to be in because here our crest cancels the trough. Lambda is exactly equal to L. So you see this happens at Froude number 0.4, okay? If you go faster, you'll end up in a bad situation here where your trough combines with the trough. If you go slower, again, not as ideal. So this is the, how do you say, the fastest speed where you're still somewhat efficient. Not talking about planing hulls, for non-planing hulls. If you start going faster, you will have this situation. Okay, so that's why this hull speed is so talked about in the boating community. All right, so let's just write down what hull speed is. What? Yes. Oh, okay. And yeah, yeah. See here, you can compute exactly the speed you should have gone. Um, well, yeah. Speed for which lambda is exactly equal to the length, right? The hull length. So the bow crest combines with the trough trough at stern. Okay. And this is what we like. So this is efficient. And this hull speed is this is the fastest. Again, remember, we're talking about displacement ships. We're not talking about planing hulls. Would you be able to find this simple formula for this hull speed? Mm, the fruit number you basically get from here, right? In this condition. So this is the only condition you are given. Yeah, you know lambda, and you know the relation between lambda and u. So it's a straightforward computation. So let's see. We can compute. Um, this constant, so yeah, let me write out two different ones. So if L ship in feet and V hull in knots. or so these are constant. G is a constant here, and meter per second squared is 9.81. If you plug that in, you get this 1.56. So if you use all SI units, this is the constant that you end up getting. If you decide to use length of ship in feet and you want the hull speed in knots, that's the constant you should use. Not confusing? Okay. Yeah, if you don't like the constant, you can just keep this formula and plug in G, do everything in meters, and then convert to feet and knots. Okay, so this is a very useful first cut approximation for a good speed to go at for your boat. Okay. Okay, any questions? All right. Let me bring back, so notice here, we have a speed and a square root of length. So this ratio between the two things is usually what's used when we plot drag on the y-axis. We have that ratio, speed over square root of length on the x-axis. Okay. So whenever you hear the term speed length ratio, that's what should pop in mind. Okay. V over square root of L. Okay, now let me, oh, I forgot to write one more thing. So just above the speed, you'll get, it'll plop down, and if you go even faster, you will start planing. Okay, let me bring back the second image now. So we talked about the first image here. Okay, so this curve is for a specific hull. If you change the hull design, the curve will change. Okay, so all right, and then let me mark a point and you tell me what you see. Okay, what do you see? Why did I mark these 2 points? Let me draw 2 more lines and then hopefully. Okay, now.
I think what we're seeing is that if you go up to about 1.8 on the speed length ratio, your drag will come back down to where it was at 1.5. So you can go at 1.8 with the same drag or power efficiency as if you're just doing 1.5.
Can't use these to predict when planing starts to happen. Okay, I don't think there's any way to predict that. I mean, exactly when it'll happen. We talked about the fruit number. If the fruit number is much larger than 0.5, you'll start planing. But this curve actually tells us if your speed ratio is 1.5, you can do much better. Either slow down, but you'll go slower, which is not good, or you speed up. And your CF, is it CF? No, CT. The drag coefficient will end up being the same. So it's preferable to go faster, okay? And you of course, you'll consume a bit more energy because this is the drag coefficient. So we have to multiply by half rho v squared. But overall, in terms of efficiency, this speed is much better than this. Okay? Speed over length, square root of L ratio, L is fixed, but V is what you change. All right. So that's why this is useful. So okay. So we're referring to the drag curve image or plot. The annotated points. What's the reason? We're going faster, but the drag is lower because humps and hollows. We don't know if it's the hull speed exactly, but we're in a hollow, all right? So the wave making resistance decreases because we get beneficial interference between the two wave systems, okay? So reason is we are operating in a hollow. Would you speed up to 1.7? No, that's terrible, right? Yeah, if you're at 1.6, okay, fine. Speeding up to 1.7 doesn't hurt that much, but you'd rather go all the way to 1.8, okay? So these curves can be very, very, very useful. So let's talk about a real world example and see how wave making affects the operation. So okay, so we have some data for a real world ship, and let's see what happens with wave drag. So the length of the ship is 125 meters, 408 feet. It has 2 gas turbine engines. That can generate 30 megawatt of power. Which is 41,000 horsepower. Okay, and we have a max speed of 29 knots. Okay, we know how to compute the hull speed for this. The only thing we need is the length, right? Okay, and if you look up the data sheets, you'll find that with just a single of the engines operating, so a single engine is basically 20,500 horsepower. The ship can reach speeds of 25 knots. What if we run both the engines? What's the speed we can reach? 29 knots. Okay, so it takes an extra 20,000 horsepower to increase the speed by 4 knots. All right. Yeah, it's just because of the wave drag. And again, remember, I mean, this hull speed formula we have is based on very simple calculations. But then in a real world hull that's very complex in shape and it creates very complex wave systems, we're close enough, 27 to 25, okay? So yeah, these estimates are very useful and relatively accurate. How would you increase the max speed of this hull? So let me rephrase that question and ask you. How can we reduce the effects of wave making resistance? Shorter hull. Shorter hull gives you what? I'm talking about the design of the hull. So this is with respect to hull design, not just operating speed. So shorter or longer?
Longer hull.
Longer hull, right? If you have a longer hull, your hull speed increases. That's why if you compute the power consumed by these very long aircraft carriers, power per ton ends up being lower than the power per ton for a shorter destroyer or a frigate, okay? Yeah, I mean, of course, the absolute power required will be much larger. We care about per ton power, all right? So that's one way. And the other way is, you remember this bulbous nose in front of the hull at the bow? That disrupts the wave system generated by the bow. So that's another aspect you can use to reduce wave making drag. Okay, so one is Okay, so see, that might seem a bit counterintuitive. A longer hull can go faster, but the reason is you have lower wave drag. Okay, so power required here is 2.9 horsepower per ton to go at 29 knots. And here you have 10.3 horsepower per ton. Okay, so much more effective to have this aircraft carrier transporting things. All right, and the other is you can have a bulbous bow. Yeah, with the bulbous bow, there's the disadvantage. You design it for a given speed. If you go faster or slower, it can hurt. Okay. So any questions? Okay, so we're out of time, and any questions about the final? Focus on things after the midterm, yes. I won't give you any integration stuff, numerical integration stuff. Any other questions about final? All right, so I'll see you April 28th, 7:45 a.m. Yeah. Okay, see you guys.